All right. I am here with Dave Beckberger, architect from the Neptune team. Dave, welcome to the show.
Thanks. Thank you for having me, Robert and Jeff.
So I hear we have some big news to announce today. Would you
Yes.
do the honors
Yes.
and let the cat out of the bag?
All right. Yeah. So actually, yesterday, the Amazon Neptune service team probably released, which was not the biggest release since we went GA, probably the next biggest release, where we actually announced a variety of different features. But probably the most important one was we actually announced support for a new query language within this. That was kind of our number one customer request, which is OpenCypher. So with this release, Neptune now supports kind of the three most popular open graph query languages: OpenCypher, Gremlin, and Sparkle. And this really is about providing our customers the flexibility to choose the language that's best for their application. With these features combined with some of the other announcements yesterday of Neptune ML going into general availability and some of our really enhanced Neptune Notebook support, we're really this really kind of shows how we're really about listening to customer feedback, taking that feedback, and really giving them the tools they need to build, graph-based applications like knowledge graphs, identity graphs, and fraud graphs on top of, our fully managed graph service.
So, Dave, this sounds really, really cool, and congrats on the launch. Maybe step back just a tiny bit and tell us why should customers care, and even better, why should they be excited about this launch?
No, that's great. Graphs and graph databases are kind of a relatively newcomer to the field, so a lot of people may have never been really exposed to them. And really, graphs and graph databases are a type of database that's really all about being able to support and work with complex data types. So, complex data types being data where the connections within your data are very important. This is really common in use cases, like I said, knowledge graphs, or which are a type of graph where you want to connect data silos together. So it's really common. A lot, every enterprise has tons of different disconnected data sets, and knowledge graphs are all about taking those. Maybe you're an e-commerce site, you have an inventory management system and a shipping management system and a customer feedback management system, and you want to link those together to kind of get a holistic view. So those sorts of things are really about that. Identity graphs are about connecting disparate data sets together, and for things like being able to uniquely identify a person within from that comes in from a mobile device or comes in from a website, in order to be able to provide things like personalized recommendations on top of it. And with this announcement today, what we've really done is lower the bar of entry for customers to be able to start building these type of applications. So OpenCypher is a graph query language that's really inspired by SQL. So it's really familiar for customers that are used to working in relational databases to be able to benefit from the advantages of graph databases on top, to build their applications faster and easier.
That's awesome. Well, before the announcement of support for OpenCypher, what were customers using, and what are the main benefits that they can expect to see here?
So with the benefits of using Neptune is prior to our announcement of OpenCypher, I should put it that way. We already supported within Neptune, which is our Neptune, which is the managed graph database service provided by Amazon. We already supported the two most common graph data models out there, those being RDF, which is a W3C standard, and property graph. For the property graph for property graphs, we supported a query language called Tinkerpop Gremlin. For RDF, we supported a query language called Sparkle, which is another W3C standard. With the addition of OpenCypher, we now have a second query language for property graph data. So you can use either, within Neptune, you can now store your data one time and use that data. You can query that data either using OpenCypher or Gremlin. So we have provided this interoperability between them. And this really is about allowing customers to be able to use those connections within their data, those complex connections within their data, to be able to answer, types of questions that are not easily answered through other types of NoSQL or SQL databases out there today.
Speaking of SQL and NoSQL databases, Dave, I think it might be a good idea to kind of zoom out a bit and talk generally about graph databases. What's a graph database, and why is it even called that?
Yeah, I mean, that's actually a really great question. When we get kind of frequent, like I said, they're kind of newcomers on the scenes. But I mean, this kind of first starts with what is a graph? And in a graph at its highest level, it's a type of data structure where you have nodes or entities, and those are connected together with relationships. Those are types, that data structure is something very familiar to developers, like, from a programming standpoint, things like trees and linked lists are a type of graph. What a graph database is it takes that ability to have those highly connected data sets, and it stores them in such a way it stores them in such a way that it optimizes the ability to use the connections between data sets to answer types of questions. So I always kind of like to talk about it as graphs make connections in data first-class citizens. So it really enables answering questions inside use cases, things, social networks, org charts, things like that. To answer questions, things like, where are the risks in my supply chain? You have this entire, supply chains kind of look a lot like a network or a tree. You want to be able to kind of figure out where are the most critical pieces inside that network, that if this goes out, I have the most risk here if this supplier, because they supply other suppliers that I also use. You use them to be able to find out how items are related to one another or how things are connected. At one point I was working in my previous job, I was working at a company that did family trees. Kind of a very natural graph, your grandparents, things like that. So being able to use that to figure out how two people in this tree are connected together, maybe they're a second cousin 4 times removed, something like that. And being able to connect, use not just the fact that people are there, but the fact that those people are connected in specific ways to be able to answer the types of questions.
So Dave, we have a lot of purpose-built databases at AWS. I'm actually pretty confident I can't name them all offhand. Where do graph databases fit kind of in the larger taxonomy of databases?
Yeah, I mean, when I kind of think of just NoSQL in general and our purpose-built database set of databases, I kind of think of them as they're all really targeted at handling some data with some level of complexity around it. So, kind of the simplest out there is something like an Elastic Cache, where it's really a key value store. So, your data inside an Elastic Cache, it's very simple. There's no connections related to it. It's an entity and it's a key in the entity associated with it. You can move on to something a little more column oriented. So you can, something like a Dynamo or a key spaces, where your data's, sort of logically stored into rows, where you have connections between data within a row, but they're not necessarily connected across, large groups of items. You have something like document databases. You can start to express the connections within your data a little more richly, but the richness of those connections is really kind of a relationship, a set of relationships or connections within that, atomic container of that document itself. Relational databases are, the steadfast aspect of, databases out there. And they're really about, dealing with entities. The connections inside those, the relations between those entities are really represented by something like foreign keys. So they're actually represented as metadata on there. So, when you actually want to go find out how 2 items are related, you join them using, an inner join or something like that. And it has to calculate those connections at the time you're processing the query. Graph databases, on the other hand, as I said, kind of store those relations between things as first-class citizens. So those data of, the fact that A is related to B is actually stored as data on disk, for lack of a kind of a better thing. So being able to use those connections to find out how those things are related really doesn't require a lot of computation, because it's data. I can just retrieve it from disk versus having to compute this on the fly. And this really becomes very important when you want to answer questions that have to do with, where the strength, weight, or quality of those relationships are really key to finding the answers to it. How are Jeff and I connected on something like LinkedIn? If I have a network diagram and my router fails, what downstream items will be impacted? To use that family tree example I was talking about previously. It was a genetic genealogy company, and we wanted to be able to answer questions like, I want to prove that my great grandfather is who I thought it is. So who is alive in my family tree still that I can get a DNA test from that will link us back together. So answering those questions where you're really looking at how those items are related together.
Yeah, looks like we had a quick connection there, but we have Jeff joining us back again. Yeah, I think you bring up a really good use case, Dave. In these cases where you're modeling something like a family tree, I can imagine that if I were to store that in a classical relational database, it's kind of taxing to imagine what the queries look like to answer some of the questions you raised, but I feel like it can be done. Whereas I feel like what you're saying with the graph database is that the model is just kind of a better fit in terms of the data representation and the structuring of those relationships. Is that kind of where you're going with this? Is that a fair interpretation?
No, I think that's definitely fair. I mean, relational databases have been around for quite a long time. People have done many, put many trees inside relational databases. This is not that's not a unique thing. People have built social networks on relational databases. But usually where they tend to run into an issue with those sorts of things is really when they're trying to ask really tough queries of those types of databases, where you want to ask something, especially something that's like an unbounded recursive traversal. So something like, how are Jeff and I connected? Well, Jeff and I could be connected via, one connection, 2 connections, 4 connections, 400 connections. We don't actually, we don't necessarily know that ahead of time. So being able to write something like a SQL statement to be able to do that requires you to write, some sort of recursive SQL, maybe a common table expression if you're familiar with that, or using with recursive at the top of your query. And those types of queries tend to be, at least from my experience working, they tend to be relatively difficult to write. They tend to be relatively difficult to understand when someone else has written them, and you have to go back and figure out why they're not necessarily performing very well. And part of that comes down to, as I mentioned, just the nature of the way data is stored in a relational database. When you're doing those sorts of joins in a relational database, it's logically, you can kind of think of it as it's building up a bigger and bigger table with every sort of join, where you're joining, a table to itself, to itself, to itself, to itself, if an maybe it's a organizational hierarchy. Within graphs, you actually kind of fundamentally work a little different. The way it stores data and the way you query that data is really about moving from one point in the graph to another. We call it traversing the graph. It's like moving from one point in the graph to another point in the graph to another point in the graph to another point in the graph. So it really works well for this.
Yeah, so, and I think that's a very different mental model that this visualization of traversing edges between nodes versus generating kind of in-memory tables or views on a table, right? Because I think that's the model that at least I mentally work with when I'm writing a SQL query. Is I've got these different tables and I'm trying to find axes on which to rotate to join these different tables. But what you're describing is something slightly different, which is, it's almost imagine like every node is just a hop, or every edge is a hop to a different node. And once you get there, you can work with the properties, or you can work with the other connections to either stay in the node or to fan out to another node. And I think that's kind of interesting, right? Because that's the thing that enables you to more efficiently answer some questions versus others. I hope I'm not too far off base there.
No, actually, what you just hit on is kind of actually one of the biggest things that, my background was coming from a relational developer experience, as I guess most everybody else's is. And that was one of the biggest kind of mind shifts to change is changing from that tabular model of everything is a row and a column to kind of a mind map model is the way I like to think about it, where, data, items are connected, and when you move from A to B, now you have a different set of connections and properties that you can look at inside, from there.
All right, so these are all like really good things that you told us what graph databases are good at. What are they not so good at? What is the counterindication that says you're somehow trying to force fit your data or your queries into a graph database?
Usually when I see, graph databases, in general, you can think of they can model most anything. They have a natural fit into the way we think and our lives are organized. Our lives are organized as networks, and they work very well for that. But they don't, they're not necessarily as optimized as some other choices for certain types of questions. The one I always kind of see is, if you wanted to do something like, give me the total of sales for the last month. This is something like, this is a set operation. This is something where relational databases are this is where they excel. They're really good at answering these sorts of questions and slicing, dicing, tables or multiple, joins across several tables in a nice denormalized format in order to return data very, very efficiently. And those sorts of things, you can model them in a graph, but generally you'll find out that it's, not necessarily worth, it's easier to do in, whatever, relational database you're probably already using on site. The other one we get a lot is time series data. So time series data with graphs can be very tricky. So one of the things about graphs is when you're working through those traversals and you're moving from point A to point B to point C, how long those traversals tend to take, the latency of those types of queries really has to do with how many things you have to touch in order to get from A to B to C. So time series data where you're, maybe it's sensor data, something like that, where you're really getting a lot of data in constantly, can be tricky in graph. Especially when you want to talk about storing like the raw IoT type data. Usually we find out that those sorts of raw IoT type data is better stored in something like a DynamoDB. But how those sensors are connected is something that really excels to be stored in a graph. The fact maybe it's sensors in an engine, and you want to know that this pressure sensor is associated with this temperature sensor in the same cylinder. So if I see if all of a sudden I see pressure and temperature go up on this one thing, this might be, I might be able to link those two together to be able to see that it's this cylinder in the engine that I want to probably look at, might be problematic, that in a way that may not be easily seen by just looking at raw IoT type data.
Yeah, I think the time series example is particularly interesting. And I want to connect this back to something you said, Jeff, which was that, here at AWS, we have a whole variety of purpose-built databases, of which Neptune is one of them, right? Neptune occupies this area where for graph-related problems, that's what it's designed to do. But especially for time series, we have another database called Amazon TimeStream, which is our serverless, scalable time series database. And that database has a whole different set of optimizations specifically for time series data. And I think, to your point, Dave, this is the reason why we have those two as even separate products, right? That's how different the use cases are, is that we see them as the use cases are so, there are so many variations of the use cases that we need to optimize them as far as different SDKs, different APIs, different vernacular, and what have you. So I think that's I think definitely if we can have a link in chat about the different database offerings that we have on AWS, I think this is truly one of the things that sets AWS apart, is our database offering. Of course, we can't really talk about databases without referencing RDS. RDS, we've been talking about relational databases, but typically when you want to reach for a relational database and you're on AWS, you reach for RDS, right? So this set of problems, what we're talking about, and the services that solve them, they're all within the realm of our database offerings on AWS. So, but Neptune, I think Neptune launched in 2018 initially, right? So
yeah, just a little over 3 years ago, we went GA in 2018.
So one of the newer databases, but absolutely important member of the family.
Well, and to that note, I mean, we often see Neptune used in conjunction with those other databases because, as you pointed out, they're very much complementary to one another. They each have their own strengths, and they each have the things they do very, very well. So being able to choose the right database for the right kind of problem or right portion of your application that you're trying to work with is really a common pattern that we see.
Before we jump right into querying, let's just kind of give our viewers just a little bit of a kind of a basic understanding of Neptune, kind of what it is, why we built it, maybe get a bit into like the serverlessness of it as well, if you like.
Sorry, I just spotted a really good question in chat. Sorry, let's continue this question right after we take a question from chat. Cameron asks, how is the performance of graph query for a complex relation compared to the SQL query for a similar complexity? And I'll add my personal interpretation of this. I think also, are there examples of queries that simply cannot be answered in one form or the other, or is it a matter of kind of optimization?
I mean, there are, I guess to answer the general question here, if you wanted to do something like, let's say, take an organization or a hierarchy, let's say it's an employee organization, you can write those sorts of queries in either an SQL type language or dialect and in a graph query. And it really comes down to, in those sorts of scenarios, the optimizations around one, not just the underlying optimizations of how the data is stored on the disk and how you actually can read the data, but honestly, it's the optimization of how that data is, how the query languages are structured in order to be able to answer those sorts of questions, and how that processing actually occurs on the actual in the query itself. As I kind of mentioned, in SQL, you're going to write some sort of with recursive query or some sort of CTE to basically loop back over this an unknown number of times. And those are not, if you've looked at them, those are not easy queries to look at, read, understand, and performance optimize. At a processing level, what it's going to be doing is it's basically each time you go through that join, it's going to be basically joining a bigger and bigger and bigger and bigger and bigger table. So it gets slower and slower and slower and slower after some point where the optimizations of SQL run out. So something like that is definitely one of those sorts of examples that SQL doesn't do great. Whereas graphs, because the query languages are optimized for moving through graphs, for moving from A to B to C, those sorts of, the queries tend to be very, 1 or 2 lines in order to be able to write them. And they tend, because you're not building a bigger and bigger table and you're just moving from A to B to C, you don't run into those sorts of limitations of having that bigger and bigger table.
Yeah, and I think I just popped up a related question here from Yifan Gan on LinkedIn. Does Neptune support general graph searching algorithms like K shortest path? And again, some context around this. There are certain sets of graph theory problems out there that are computationally intractable using traditional methods. And I think the question is also very related to what you were talking about, which is that, yes, you can write long nested with recursive SQL queries, but there's also kind of a computational element in terms of just, upper bound and complexity. So, what are your thoughts on this question?
Yeah, I mean, they're something, the short answer is yes, you can, in Neptune, you can do shortest path type queries in actually, in either OpenCypher or the Gremlin query language if you're using our property graph data model. And they're actually pretty straightforward to write because those sorts of questions are very much around the moving from A to B to C. What's the shortest way I can get from A to B or A to C in this case, I guess. To answer the bigger questions, yeah, there are definitely types of questions that graphs in general work very, very well on. Some of those questions are extremely computationally complex. It's very easy in a graph to get into like NP hard or NP complete type questions. Those sorts of questions, if you wanted to run something like let's just say you wanted to run a graph coloring algorithm, which is a very interesting graph coloring algorithm, but I think I can't remember if it's NP complete or NP hard, but it's a very complex one. Those sorts of algorithms are not ones that, Neptune is really optimized for, because those sorts of algorithms are usually better run in something like a batch system, maybe something like an EMR that we've worked with customers on. Neptune really is optimized to be able to work, handle transactional type queries of, find me Jeff and everybody that's connected to him, or how Jeff and Robert are connected, those sorts of things. Neptune is that perfect purpose-built graph database that we have that's really I targeted at those transactional graph use cases that we're kind of talking about. It's meant to be there to answer questions that you start at like one location, 1 or 2 vertices or a small set of vertices and traverse out from there, versus some of the other ones we can graph global queries where you want to answer something across the entirety of the graph. PageRank being an example like that. When we work with customers with PageRank, usually what we end up finding is that we work with some combination of Neptune to store it to serve their transactional needs, and something like an EMR to be able to run those sorts of large scale analytics that you don't usually always want to run very frequently, but you might want to store and augment those results back into your graph to be able to use those for a transactional purpose.
All right, last question, I promise, and then we'll get back on to the Jeff's question, which Jeff is patiently waiting to be answered. But Lauren Ferrer asks, from LinkedIn, asks, node read capacity or write capacity, RCU, WCU, to provide? I think we can address that offline as far as how capacity works. But the more interesting part of this question, I think, is always strong consistency read. And I'm going to flesh this out a little bit. I believe what Lauren is asking here is, can you read your own writes when you commit a transaction to Neptune? And then, depending on yes or no, zooming out a little bit, generally speaking, what kind of database is Neptune? Is it kind of an eventually consistent database? Is it one that kind of, is closer toward the ACID style of database, or how does it behave with respect to the CAP theorem?
Yeah, no, it's a great question. So Neptune is an ACID compliant database. So when you write a transaction, you can read that back immediately from the writer node and be able to have a strong consistency. We do have the concept of read replicas. So Neptune is an instance-based database where you have one writer and you can scale up to 15 read instances. So you can each of those read replicas basically does have a very small in the terms of millisecond latency in order to get that data and get the newest data. So it's it's strongly consistent in terms of the writer, and there's a minimal amount of eventual consistency across each of the read replicas. To answer that at a high level.
Yeah, I think that's it. Well, we've reached the end of the question queue, so let's get back to answering Jeff's question finally.
All right. So first of all, Rob, you promised me no math, and our first episode, and we're talking NP complete. So
yeah. Hey. Hey, actually, I think it was Dave that brought that up. I didn't say that. I didn't say those words. So
I brought that up.
Now that I'm in marketing, all those brain cells have been reclaimed for other more nefarious purposes. But
okay, we'll just say very, very hard.
Yes, perfect. So anyway, Dave, I think you kind of answered this already, but you talked about read replicas and scaling and so forth. But how should our audience kind of think about Neptune as kind of instance-based or serverless or somewhere in between?
Yeah, it's an instance-based database. So you basically do specify kind of what the topology of the cluster you spin up is. So, you spin up inside a region, you can spin up a Neptune cluster. As I said, kind of that Neptune cluster is instance-based. You have one write instance. Those can be scaled vertically. So we do support scaling anywhere from a T3 medium for something like a development workload. You just want to try it out, see how it works, see what you can do with it, up to an R5 24XL for our largest, highest end workloads. Then you can also actually scale. You can scale it. The read replicas both horizontally and vertically. You can scale up to 15 different read replicas, and then within each of those instances, you can scale it from the same size, from a T3 medium up to an R5 24XL. And this really, part of this also comes down to the nature of the way graph questions are usually answered. Graph questions tend to be the types of questions you want to answer with a graph tend to be very read heavy, because let's be honest, you want to read the connections between things. You're going to write one thing one time, you might update it every once in a while, but you're going to use that connection to connect things, or use that entity to connect things together much more often than you're going to be writing them. So that we provide that read scalability to be able to handle those sorts of the read heavy side of that workload.
Dave, you mentioned earlier that you saw customer use cases that combined the strengths of Neptune with the strengths of some of our other purpose-built databases. Can you talk a little bit more about that?
Yeah, like I said, we not most of the time, but frequently when we go into customers, they either have a workload in something like RDS or a workload in something like DynamoDB, and they're running into parts of that workload, parts of that application that they're not easily able to answer in those sorts of things. Maybe these are the types of questions we were talking about, the ones where you're using the connections between data in order to be able to answer them. So we work very well on both sides of this, where we work with RDS, and we can have patterns and reference architectures out there to be able to kind of work with RDS, take data out of RDS, put it into Neptune, be able to use that data for querying, using them in conjunction with one another. We see that frequently with something like RDS or DynamoDB. We can also do it the other way, where we have data stored in Neptune and feed that into downstream systems or downstream processes through our Neptune Streams interface. So Neptune Streams is basically a change data capture or a CDC type feed off of it, where as you're changing data in your graph, you can get, you basically will get an event that you can look at, a notification, you can pull a stream and basically get the change that happened and use that to trigger some sort of downstream process.
So let's talk a little bit about scaling and scalability. You talked about the fact that we can change the instance size on our clusters. We can have lots of read replicas. I get that. What do you consider kind of large and amazing and awesome and kind of at the frontier of possible when we talk about, I don't even know quite what metric you'd use to measure the scale of these different problems. Like what can Neptune do and how big can it grow, and where are we?
Well, I think one of the unique aspects of Neptune is the way that we've architected the database itself. We've actually separated out that graph computing layer that's doing those processing queries from the storage layer. So those two things can sort of scale independently as you need. With the storage layer, when you start writing the data into Neptune, you basically get a 10 gigabyte data chunk that auto scales as you add more and more data. So as you add more and more data, it will basically add another 10 gigabyte chunk and go up like that, up to 64 terabytes. With that size data, we can store tens of billions of relationships and these sorts of things of nodes, relationships, and properties. You know, they're kind of all that's usually the way we talk about the size of our database. But I think that unique aspect that storage is decoupled from compute really gives the customer the ability to know that they don't have to necessarily know that, oh, well, they don't have to provision all of this infrastructure up front to be able to, you know, store what they think they might have for data. You kind of, well, you know, from a storage perspective, it will scale as you add more and more data, and you can, you know, then change the instance size to really right size the workload that you need, or right size for the workload that you're running on.
Yeah.
So what kind of things are our customers doing that are at this kind of scale?
We have a couple of customers, you know, we have customers like that are building things like social networks and huge knowledge graphs, you know, so there we have, you know, worked with customers like Nike, FINRA, Netflix, and Yahoo Knowledge Graph on working with data at these sorts of scales of, you know, billions, tens of billions of relationships, many terabytes of data in order to answer, you know, in order to be able to serve out those sorts of, answer the sorts of questions and serve out the information they need.
Awesome. Well, I'm kind of curious, and we talked a lot about the differences in the querying patterns, the mental models when you're using graph databases. What does a graph query even look like? And can we compare it to you know, you said this OpenCypher, for example, looks a lot like SQL. Can we compare a SQL query and a OpenCypher query for a graph database side by side and see how that looks?
Yeah. If we want to flip to some of these slides, I can show you what these kind of look like for a really common use case.
Absolutely. Are you ready to screen share?
Yep.
Okay.
All right. Yeah. So, you know, you kind of look at this, think about this as in a common use case. In this case, it's, we're sitting there looking at something like an organizational hierarchy within, within a business. Well, you know, if you're going to put this in something like a relational database schema, I'm sure we've all done something very similar to like this. You know, obviously this is a little bit of an overly simplified version of a relational schema, but you know, you have an employee ID, you're going to have something like a name, and then you're going to basically have a foreign key back to the same table where you're kind of looking through that. You know, your data is probably going to look something like this in order to be able to answer that. So in a graph, if you take the same thing, you know, your graph schema looks like this. It's basically going to be one node or vertex type. In this case, it's employee with one connection back, which is basically is going to be works for. The data that you actually store in the database is going to look very much like this. It's going to look very much like the domain in which you're actually working in. It's going to be very much look like this sort of tree that you're, that you're probably, your mental model is probably familiar with. So what does it look like to actually basically answer the question of what is my reporting hierarchy? So what you're looking at here is basically that sort of recursive SQL or CTE type thing, where you basically need to go in, create this complex query in order to be able to answer this by joining together the same table an unknown number of times in order to get from a person A, in this case, to the CEO. What you're looking at here on the other side is the equivalent in the graph query languages. So at the top, we have OpenCypher. OpenCypher, as we mentioned, it's a declarative graph query language, much like SQL, where you basically, this looks probably familiar to you, and I don't know if either of you have ever even looked at OpenCypher before, but you probably immediately can kind of understand what it is using, because of this, you know, the pattern matching type syntax. So, you know, it starts with this match clause, where basically you're kind of specifying this ASCII art or motif type thing that shows you how you're going to work from one customer, or how you're going to move from, you know, in this case, a node of an employee all the way across a works for edge to another node. So when you're looking at OpenCypher, anything that's kind of in a parentheses, it represents a node or a property on, you know, a filter that you want to put on node. In this case, I'm saying I want to match on, you know, I'm going to give an alias of E to the first node, and it's going to be an employee. And then I'm going to move out across an edge for a works for edge to another node. The little star you see in there basically says, do this repeatedly. So that's the recursive part here. This is going to keep doing it, and this is going to keep recursing across that sort of pattern until it gets there. You know, the next part is a where clause. This probably looks very familiar for anybody familiar with SQL, where I'm saying, for where I want to start on something where the, you know, the E, so that first employee I'm starting with has a name of you. And then I want to return that basically the path of data, or the connection, or the set of vertices and edges I used to get from one point to the other. So that's kind of what OpenCypher looks like. The bottom is our Gremlin query. Gremlin is a slightly different type of language. Gremlin is an imperative query language. Looks a lot like programming. If you're familiar with something like Java Streams API or a link in .NET, it really has that kind of feel to it, where you're really kind of specifying, as opposed to OpenCypher, where you're basically specifying, find me something that looks like this pattern. In Gremlin, you're really specifying, I want to start at a specific point and how you move through the graph from one point to another. In this case, it's saying I want to start at an employee that has a name of you, and then I want to repeat out the works for edge and return the path. So that's kind of, fundamentally what some of the difference in the actual query languages look like compared to, SQL, and how they're kind of processed.
So quick question here, Dave, for the Gremlin query where you say v dot has, v is for vertex, is that?
Yes. So kind of the way that the Gremlin works, it starts with this concept of G, which is basically, you can kind of almost think of as given your graph, I want to get all of the vertices associated with it, which is what the V is. You can actually start on your edges too. So if you have, because they're treated as first-class citizens, you could actually start on a connection within your graph, a relation within your graph that, and start out from there.
Got it. So what you're saying with the Gremlin query is you're starting at vertices that match the predicate of having employee name and you. Is that how I read that? Is that or
that's exactly the way to look at it there. I actually noticed now that I look at this, of course, demo bug Gremlins. I noticed that in the repeat, I'm missing a step in there that basically says it should say repeat parentheses out works for, and then a close parentheses to basically say, I want to go out. I want to basically traverse out the edge of works for.
And so
that's how it's live.
Hey, you could probably tell us that this is a valid Gremlin query, and I don't think we'd be able to challenge you on it. But
somebody that knows Gremlin would call me on it.
We won't tell. But let's. I mean, I think the point here is very interesting, right? Because let's actually just appreciate what's going on here. On the left, you have this frankly very busy SQL query. I've seen busier, but I cannot say that I've ever had a good time dealing with this kind of thing. Maybe I'm just bad at SQL, but it's pretty clear that even without knowing Gremlin or OpenCypher, the intent on the right is a lot more crisp. In other words, we have a lot higher signal to noise ratio in the code. And that's everything, right? I mean, you may have heard this very famous statement that's like, code is written first and foremost to be read and incidentally to be executed. And I know that that's pretty controversial. That's a hot take, but this makes a huge difference, right? Imagine you write a query like this, and the query starts to power some sort of critical business workflow. 10 years later, who's going to be around to maintain that, right?
Well,
and how easy is it to kind of spot by inspection whether or not the code is doing what it should do, and therefore take the right level of maintenance precautions like that? I think that is the understated power of having the right tool for the job here.
Mm-hmm. Yeah. Well, when I look at the query on the left, I look and say, once I had one of those in production, I would be unbelievably reluctant to make even the slightest change to it, because the intent is not at all clear, and it seems like some of the magic is somewhere in that inner join, somewhere deep 2/3 of the way through. But the fact that you can look at either of the OpenCypher or the Gremlin, and the overall intent is pretty clear and pretty obvious. And if you were to make a small change, I think it would be pretty obvious what the impact of that change should be, versus the fact that we've kind of like forced this SQL, this relational table to do something it can do, but it's not truly great at.
Absolutely.
Yeah. I mean, if you wanted to, let's just say if you came in and you were either a new developer on the team, or you were handed this code because the person, previous to you two moved on to something else, and you just needed to make a simple change of maybe you not only want to start at a person with the name of you, but you want to start where that person also had a start date in the last year. Pretty sure you probably could either work with either the OpenCypher or you'd understand how to add that to OpenCypher or Gremlin a lot faster than you probably would with something like that SQL query.
Chat, yeah, and let us know. I'm curious, if you were just hired at a new company, you're starting a new job, and you had to maintain a query, which one of these would you prefer to maintain? SQL, OpenCypher, or Gremlin? Let us know.
Or if you've worked at a company and had this question.
Yes. Yeah, exactly. So there's just one question before we move on from this slide that I want to get clear for my edification. So it looks like the predicate in Gremlin is kind of doing some sort of duck typing, right? It's saying when you look for edges and properties with these things, then you know you've found the right vertex. Whereas OpenCypher seems to have E:employee, which is kind of a more type safe match for finding the node. Is that what's going on here, or am I reading this all wrong?
Actually, in this case, they're both basically doing the functionally same thing. They're both so inside property graphs, which is what OpenCypher and Gremlin are based upon, are the languages you can use to query them. That you have this concept of a node label, which you can kind of think is a grouping of types of things. So in this case, both of them are saying, within a graph, you can have many different types of entities and a lot of different complex relationships. You group them together by labels to make them essentially easier to look up and find. In this case, I'm basically saying E:employee, saying give me all of the, I only want to look at the employee nodes in my graph. If you have company nodes or you have other types of nodes, I don't want to look at those in order to traverse this pattern. In Gremlin, you're doing the same thing with that, that has pattern. It's basically saying, you can kind of think of this as two filters together. It's saying, for all the vertices, only look at the ones that have a label of employee, and then only give me the ones that have a name that's equal to you. So it's just kind of a little handy, way to be able to, condense your query down so it's more readable. Looks like OpenCypher is definitely the preference of at least code hustle.
Not surprising. Yeah, I mean, they're both just so much simpler than what we would have had to write before we had access to tools like these. So this is great. Let's keep going.
Yeah, well, I also want to kind of mention, I think one of the unique things about Amazon Neptune's implementation of OpenCypher is you can use both of these on top of the same data. So you store your data in the graph once, then you can choose as the developer which one is going to answer your question better. Or do you want to go with OpenCypher for this sort of question, or do you want to use Gremlin for this sort of question? And you can use it without having to do, migrate data across databases. You don't have to do all that. You can do that inside the single thing and pick and choose the right choice for your application.
Absolutely. Well, can we see some of these queries in action? Do we have an example? Maybe we can flip over to a demo and see.
Yeah.
Oh, there you go.
Yeah. So what we're going to be looking at, here's a couple of different things. We're going to be looking at what we call Neptune Notebooks, which is our customer tool set that we provide. It's provided as a set of Jupyter Magics, if you're familiar with that. So Jupyter is a notebook environment that we can either run hosted inside AWS using our Neptune Notebooks. You can run this, or you can run on your own machine or an EC2 instance. And what the Neptune team has provided is an open source set of magics, which are basically, you can think of them as little commands that will basically allow you to interact with the data. Allows you to basically, we'll walk through a couple of them here, but allows you to do things like, I want to be able to run queries. I want to be able to load data into my database. It's sort of the IDE interface that we provide into Neptune. As part of that IDE interface, what we actually provide is a set of getting started notebooks. A set of notebooks for people that are not necessarily familiar with Neptune and how to, or graph databases in general, and to be able to use those together to be able to start doing the types of queries we're talking about here. So we have a set of getting started ones, which are very introductory type ones. We have a very rich visualization, which we'll show here in a minute, that we kind of have some notebooks that walk through all the different types of customizations you can make across them. And we have a set for our machine learning, our Neptune ML integration. But what we're going to look at today is we're going to look at, we have a set of use cases out there for our three most common use cases, being fraud graphs, knowledge graphs, and identity graphs. We're able to click into that and...
Hey, Dave, before, yeah.
Exactly
what I was about to say.
A little bit bigger. Sorry about that.
Yep.
So we have a couple in there. We just added this one as part of our release. We added this knowledge graph one in OpenCypher. This is available if you go spin up a notebook today, or you install this on your own instance. So this is an open source PyPy package, so you can just pip install graph-notebooks, and as long as you have connection into a Neptune cluster, you can be able to run these sorts of queries. So if anybody's interested in following along, this is available today. Because I'm going to skim over parts of this. But basically what each of these sort of use case notebooks really kind of does is you can kind of see it has a whole background around the type of use case. In this case, what is a knowledge graph, how you get started. We're able to go through and do things like we have a set of pre-built data sets in there. So we have data for you if you're not used to using graph databases to be able to get started with today. You can go in and just run these, we call it the seed command, to populate your data with a small data set that you can kind of get your hands on and start to see these types of queries that you can answer with graphs. In this case, it's actually a set of data that is extracted out of AWS blog posts. So we scraped the AWS databases blog for Neptune. We were able to extract out things like posts, the authors, and tags associated with those. We actually ran the posts through Comprehend, and we're able to use the post text to extract out a lot of other information, things like locations, dates, organizations, things like that, to really kind of start to connect these different posts together in ways that may not be obvious, which we'll kind of show here in a minute. So you can come in here and you can actually run and do this. So what we offer is this set of magics. You said one of them is OC or OpenCypher. You can actually works with either of those. And this is a really kind of very basic, simple OpenCypher command to basically find all of the authors which have a name of Dave Beckberger and the post that they have written. So you can come in here. We can run this. You have a couple of different tabs here. You have this console tab, which kind of shows one line per result that was returned. We have this JSON tab, which really shows the actual raw JSON that's being returned from Neptune. So with OpenCypher, we have two ways you can interact with it. We have an HTTPS endpoint that basically allows you to use a REST style call to post a query and get the results back. The results come back in this JSON format. We also support the Bolt protocol for customers that are migrating applications from some other graph databases that use Bolt to make that process simple. In this case, we're using the HTTP endpoint. So you can see this JSON format. This is a type of JSON format that I love working with as a developer because I can, in Python, do something like JSON.loads, and I'll have a map of things. I don't have to do a lot of work to push data from A to B, things like that. We have a query metadata tag, which just has a little bit of basic information about the query that was executed. And then we have the one that we kind of really wanted to show, which is this graph tab. This graph tab really shows a visualized representation of the data that was returned. So a lot of graph queries, because you're dealing with connections, because you're dealing with that sort of mind map, lend themselves very well to this sort of visualization. So with this sort of visualization, out of the box, we get this sort of grouping by label. So, in this case, you can see we have 4 posts that are shown in yellow and an author that's shown in blue. We can come in here, we can click on this. We can see the types of data and titles, the sorts of properties like post date and title that were associated with it. We can, click on the edges and see the properties associated with that. So, this is kind of a very basic one, but you can kind of start to see the power of being able to visually see your answers. We also have the ability to add a lot of customization to this. Customers constantly want to be able to say, I want to look at this data, but I want to look at it in this very specific way where I have, where I'm able to specify which property I want to be shown as the text that's being displayed, or which one I want to show the edge to be displayed. I want to be able to change this to be able to run things like, to be able to show things like I want things to be shown with certain colors or certain icons or images associated with it. And with our Neptune Notebooks environment, we support that. So in this case, I ran a slightly different query where I was basically finding all of the items associated with a specific post. So this is often this sort of query. It's called a first neighborhooding graph, which is basically give me something and all of the connections to it. And this is really common in something like customer 360 use cases where you want to get a holistic view of how a customer has interacted with a system. We're able to show that in a really visual way where you can kind of see, with these customizations, you can now see that this post has 3 authors associated with it and a variety of different organizations and tags associated with it. So those are sort of some of the kind of unique queries that we have. But really, graph queries are really all about being able to answer questions about connections between things. We can answer simple questions using things, like find me all of the co-authors for this post and how they're connected together. We're able to do that and be able to visualize those sorts of results. And you can kind of start to see the power of being able to visually represent these sorts of connections between data, because, not only can we see that, let me zoom in a little bit, that Dave Beckberger, Karthik Bharathi, and George Karapis basically worked on this specific blog post together, but we can also now see that Karthik and George have worked on another blog post together. So you can start to build this set of unknown, these potentially unknown connections between your data that you weren't able to see previously. As we mentioned, this is perfectly interoperable between both Gremlin and OpenCypher. So I can basically run that exact same query in Gremlin and get back, as you'll see from the data, the exact same answers. So I'm able to basically run these things, choose the one that's best fits the type of interest, questions I'm answering. So what type of questions can you answer with these sorts of things? Up to now, we kind of, especially with knowledge graphs we're talking about here, connecting entities together or stitching entities together in ways that you're not necessarily aware of is a really common use case. Not all of the types of questions you need to, or not all of the types of answers you get out of a graph database have to be those very visual ones. In this case, maybe I just want to be able to find out, given an author and everything that they've written, give me, the number, what's the most common stuff they write about. Maybe I want to find out, what's the most common topics they write about here. I'm able to do that pretty easily and straightforward. And in this case, instead of getting back a graph of data, I'm getting back, tabular data. I'm getting, AWS is the most common thing that I write about, things like that. You can also write more complex queries where you're starting to be able to write data where what are the most common topics that co-authors of a specific person write about, things of that nature. So you're able to kind of use this pattern matching syntax, combine it together to answer more and more complex questions. As you can see, if yet again, this is really, you start to see a lot of things that are kind of look like SQL. You see order bys, you see where clauses, things that are very familiar to developers today. Can jump ahead a little bit. Like I said, this notebook is available for anybody looking out there. But one of the other kind of common things you want to be able to answer is like unknown connections. How are China and Ohio connected in Neptune database blocks? Things you just wouldn't expect to be connected in any kind of specific way are the types of questions you can answer with graphs that are not necessarily easy to do with some of the other technologies we talked about. You're able to come in here and you start to see that you can get some very complex and very large networks of connections between things that you aren't necessarily expecting to have that sort of thing on.
Dave, I hope you know what you've done here, because you've just opened Pandora's box. I mean, Jeff Barr here is the OG AWS blogger, and you've shown him how to find hidden connections in the blog data set. I'm not sure this was a great idea, Dave. I think you should have thought this through.
I was thinking the exact same thing. Dave, I do actually have one question. You've shown us queries that retrieve data from the graph. But at the beginning, I think you showed us a command that was called seed that was like loading up the graph into Neptune.
Yes.
So are both of these query languages basically designed for literally for querying, or can you do updates, or can you like run a query and then generate a new graph as a result of a query, for example?
No, that's a good point. All the ones I've shown so far are really just read queries around it. But these graph query languages are fully built to be able to add nodes and relationships between them, things of that nature. So you can perform all of the sort of CRUD operations that you would expect on any database using any of the three query languages that we support today.
Great.
So yeah, I don't know that I had any other kind of demo things I wanted to say today. Any is there anything kind of specific that you kind of would like to think or talk about, dive into deeper?
Just an observation. I think the when you were showing us the visualizations of any one of these graph visualizations, I think this is to me this seems to be related to the point you made about the fact that in a relational database, a foreign key relationship is effectively metadata, right? I mean, you can enforce it as constraints, sure, and you can have transactional consistency that way. But it sounds like we have the best of both worlds here, where not only do we have that kind of relationship expressed in a way where it's more than just metadata, but also that lends itself to visualizations like this. I can imagine that if I were to build this from scratch with a SQL database, this is a lot of work, whereas I have this kind of at my fingertips.
Yeah, I mean, when you're working with data, and especially when you're working with graphs and talking about paths or those connections between things, you aren't building that bigger and bigger table. You're basically saying, in this case, the vertex of China is literally connected to this one that's literally connected to here, that's connected to here, that's connected to here. So you're working across those connections in order to answer the questions.
Yeah. Well, awesome. Is that all for the demo, Dave?
Yeah, that was all I had to kind of demo today.
Okay, I'm going to stop sharing your screen now. Do you have any parting thoughts for the audience on how to get started with Neptune? I know we've been posting a couple of links in here. We've had so many good questions, and I apologize I couldn't get to all of them. This is probably one of the most amount of feedback we've gotten for a guest segment in a long time. So absolutely keep the questions coming. I promise I'll do my best. I'm not sure I can get to all the questions, but they're great, and we'll follow up with you if you have something that you need help with, for sure. But yeah, any parting thoughts?
Yeah, no, that's great to hear. I'm actually glad to hear there's lots of questions. That's always, love that engagement. I mean, I think, what as we said, this is, we just announced OpenCypher support yesterday. It's, it's day one for OpenCypher on Amazon Neptune, both physically and actually. We just announced it yesterday. So, we're really looking forward. We've released this as a lab mode feature, so it's out there today with a core set of features that we're really looking for customers to give us feedback on. So please go out, try this, let us know what we can do. We're working towards, getting this, we have, a set of, OpenCypher is a big spec, and we have a set of features to be able to work on it. So what we have today is we know it's by no means yet complete, but we're really looking towards having customers give us feedback, helping us actually determine prioritization on this, because we want to iterate on this as much as possible. We have we plan on having OpenCypher generally available later this year, and in that time, we're looking to make significant language and performance improvements on kind of how it actually works today. So we're really excited to get feedback from customers, and would love to have you and your audience kind of try it out and let us know what you think.
All right. Well, David, thank you so much for being here. I learned a lot. This was truly a wonderful segment, and thanks for being on the show with us.
Oh, thank you for having me.